A transparent fish with a skull. You can see through drifts in total darkness. Nearby, a ribbon-like body, several meters long, pulses slowly, glowing faintly as if lit from within. Far below that, a creature with no eyes at all crawls across the seafloor, sensing the world through vibrations rather than sight. These animals are real, observed by cameras and submersibles, not imagined. And they are not exceptions, they are clues. As we descend into the ocean, the living forms we encounter become progressively harder to recognize. Limbs stretch, mouths widen, tissues soften, and symmetry begins to fail. Some animals appear unfinished, others exaggerated, others almost abstract. Yet each one survives in conditions that are precisely measured and consistently hostile. The deeper we go, the less life looks like what we were taught to expect. Why does depth seem to rewrite the very shape of biology? At around 200 meters, sunlight nearly disappears, pressure doubles, and temperature begins a slow decline. These are not dramatic changes to an instrument, but they are dramatic to a living cell. From this point downward, the ocean becomes a place where surface rules quietly stop working. Species still follow physics and chemistry, but not in ways that feel intuitive to us. Something fundamental shifts, and appearance is the first signal we notice. This video explores why deep-sea creatures look more alien the deeper you go, not as a matter of speculation, but as a consequence of environment. Light fades, energy thins, pressure rises, and time stretches in ways that reshape bodies and behavior alike. What seems strange at first glance turns out to be logical under extreme constraints. And once those constraints are understood, the real mystery is not how alien these creatures look, but why we ever expected them to look familiar at all. The descent begins gently, almost deceptively. Between the surface and about 200 meters, temperature drops gradually, pressure increases at a predictable rate, and sunlight weakens without fully vanishing. To human instruments, this zone still feels manageable. But to living organisms, it marks the first point where long-established biological strategies begin to strain. Familiar fish still swim here, yet subtle changes are already underway. In this layer, often called the twilight zone, light no longer behaves as it does above. Reds disappear first, then oranges and yellows, leaving a dim blue haze. Animals that rely on color for camouflage or communication lose a major advantage. Some species respond by becoming silvery and reflective. Others turn deep red, exploiting the fact that red light no longer reaches them. Even here, appearance starts to diverge from surface expectations. Pressure at this depth is roughly 20 times greater than at sea level. That increase may sound incremental, but it alters how proteins fold, how membranes behave, and how gas-filled spaces function. Swim bladders, so common near the surface, become liabilities. Many species reduce or abandon them entirely, subtly changing body shape and buoyancy. These are small adjustments, but they signal a larger biological negotiation taking place. Behavior shifts alongside anatomy. Predators begin to rely less on speed and more on ambush. Prey species reduce movement, conserving energy in a darker, colder environment. Eyes grow larger relative to body size, not because the world is darker than we imagine, but because every photon becomes valuable. Even at this early depth, the cost of seeing, moving, and feeding starts to rise. What makes this zone important is not how extreme it is, but how quickly familiarity erodes. The animals here are still recognizably fish, still within the bounds of surface biology, yet already trending towards something else. If such visible changes occur so close to the surface, it raises an uncomfortable implication. If this is only the first shift, what happens when the environment stops offering even these compromises? Below the twilight zone, light does not simply fade, it collapses. By around 1,000 meters, sunlight is functionally absent, confirmed by repeated optical measurements showing zero usable illumination. In this environment, vision becomes optional rather than essential. For some species, eyes grow enormous, capturing the faintest bioluminescent flashes. For others, eyes shrink, degrade, or disappear entirely. Both strategies solve the same problem in opposite ways. Bioluminescence replaces sunlight as the dominant visual signal. Many deep-sea organisms produce their own light through chemical reactions that are remarkably efficient. This light is used sparingly, often for luring prey, signaling mates, or confusing predators. What matters is not brightness, but contrast. Bodies evolve dark, absorbent surfaces to erase silhouettes, while glowing organs appear as isolated points in the void. This scarcity of light reshapes behavior in ways that are less obvious than anatomy. Movement becomes deliberate and minimal. Sudden motion risks revealing one's position, while constant motion wastes energy that cannot be easily replaced. Encounters between animals become rare, and when they happen, they are often brief and decisive. In such conditions, the ability to remain unseen may matter more than speed or strength. Human perception struggles here because our visual system assumes continuous illumination. Cameras require artificial light, which alters behavior and appearance the moment it is introduced. Many of the alien features we notice are not meant to be seen at all. They exist for a world where light is an event, not a background condition. This mismatch between observer and environment distorts our intuition. As visibility vanishes, appearance becomes less about display and more about function. Shapes stretch, compress, or fragment based on how organisms sense rather than how they look. The deeper problem is not darkness itself, but what darkness allows to disappear. When vision loses dominance, other forces begin to guide evolution, and they operate on scales we are only beginning to recognize. For decades, scientists believed deep sea life was sparse, scattered thinly across an enormous volume. Early nets came back nearly empty, reinforcing the idea that little could survive in such conditions. That assumption began to collapse only when acoustic surveys revealed vast layers of living biomass moving slowly through the water column. Entire ecosystems had gone unnoticed, not because they were small, but because they were difficult to measure. This phenomenon, now known as the deep scattering layer, stretches across the global ocean and migrates vertically every day. Trillions of organisms rise hundreds of meters at night and descend again by morning, forming the largest daily movement of biomass on Earth. Yet for much of the 20th century, this living layer was mistaken for the seafloor on sonar screens. Scale itself had hidden it from us. Within this moving mass, body forms reflect a different set of priorities. Many animals are small, gelatinous, or partially transparent, reducing visibility and energy cost. Density is low, not because life is rare, but because spreading out reduces competition. When humans finally observed these organisms in situ, their forms appeared strange only because they had evolved outside our sampling assumptions. Numbers change perspective. At depths where individual encounters are rare, populations still number in the billions. Reproduction, feeding, and predation occur across immense three-dimensional space rather than along a surface. This dilutes familiar patterns of territory and interaction, favoring bodies that can survive long intervals between events. The result is life that looks unfinished, stretched, or fragile, yet persists on a massive scale. What makes this realization unsettling is how long it took to arrive. If such a dominant biological structure could remain effectively invisible for so long, it suggests our understanding is shaped more by method than by reality. And if entire layers of life escaped notice once, it is reasonable to ask what larger or stranger systems may still exist below, beyond the limits of our current tools. At 1,000 meters, pressure reaches 100 times that of the surface. At 4,000 meters, it exceeds 400 times. Under these conditions, gases compress into liquids, rigid structures fail, and familiar biological materials behave unpredictably. From a surface perspective, life here should be mechanically impossible. And yet, it persists, forcing a reassessment of what biological stability actually means. Pressure does not crush organisms uniformly. It infiltrates them. Every cell, membrane, and protein must function while surrounded by immense force. Gas-filled cavities vanish entirely, which is why deep-sea animals lack lungs, swim bladders, or rigid air spaces. Instead, bodies become fluid-rich and compressible, equalizing pressure inside and out. What looks soft or shapeless is often a precise solution to a brutal constraint. Temperature compounds the problem. In much of the deep ocean, water hovers just above freezing, slowing chemical reactions and metabolic processes. Enzymes that function efficiently at the surface would stall here. Deep-sea organisms modify their molecular structures, producing proteins that remain flexible under both cold and pressure. These changes are measurable in the lab, yet their full consequences in living systems remain unclear. Skeletons, where they exist at all, become reduced or radically altered. Bone and cartilage give way to lighter, less mineralized frameworks or disappear entirely. Some animals rely on internal fluids and connective tissues for structural support, creating bodies that would collapse in shallow water but remain stable in the deep. The environment itself becomes part of the organism's architecture. This inversion of structural logic explains why deep-sea animals often appear distorted when brought to the surface. Without pressure, tissues expand, organs shift, and forms degrade. The alien appearance we associate with depth is partly a consequence of seeing these bodies outside their native conditions. What seems monstrous may simply be miscontextualized. As pressure increases further, beyond depths humans can routinely explore. Even these adaptations approach their limits. Life continues, but in forms increasingly unfamiliar, pushing against physical boundaries that seem absolute. The question is no longer how organisms survive pressure, but how much biological flexibility remains before structure itself ceases to be possible. Some deep-sea bodies challenge not just intuition, but basic anatomical logic. Mouths larger than the rest of the head, stomachs capable of expanding many times their resting size, and muscles so loosely arranged they appear unfinished. These features seem excessive until the environment is considered. When meals are unpredictable and rare, missing an opportunity can be fatal. The body becomes a contingency plan rather than a refined instrument. Lab analysis shows that many deep-sea animals operate with reduced muscle density and slower contraction speeds. This would be a disadvantage near the surface, but at depth it lowers energy demand and resists pressure-related damage. Strength gives way to endurance and flexibility. Movement becomes less about force and more about timing, drifting, and sudden activation when conditions align. Some species abandon symmetry altogether. Appendages vary in length, organs shift from typical positions, and growth appears uneven. This is not developmental failure, but tolerance. When survival does not depend on precise balance or appearance, the body can afford irregularity. Evolution favors what works, not what looks complete. Transparency is another adaptation that feels counterintuitive. Many animals reduce pigmentation and tissue density until internal organs are partially visible. This minimizes shadow and reflection in a world dominated by bioluminescent flashes. To human eyes, such bodies appear fragile or unfinished. In context, they are optimized for near invisibility. Perhaps most unsettling are creatures with minimal sensory equipment. Reduced eyes, simplified nervous systems, and limited behavioral repertoires suggest a trade-off we rarely consider. When information is scarce and encounters are infrequent, processing less can be an advantage. Complexity becomes costly. These bodies persist not because resources are abundant, but because scarcity shapes every decision. As depth increases further, even these extreme adaptations face diminishing returns. When food input approaches zero, the question shifts again. What kind of life can exist when energy itself becomes the rarest substance in the environment? In the deep ocean, food does not fall steadily. It arrives as an accident. A dead whale, a sinking plankton bloom, or fragments of organic debris drifting down from thousands of meters above. These events are rare, irregular, and often separated by years. Entire ecosystems organize themselves around waiting. Survival here depends less on finding food than on enduring the absence of it. Many deep-sea organisms operate at metabolic rates far below those of surface animals. Measurements show heartbeats that slow to near stillness and growth rates that stretch across decades. Energy is conserved not just through behavior, but through time itself. Life continues, but at a pace that feels disconnected from human experience. Some species rely on chemosynthesis rather than sunlight, drawing energy from chemical reactions around hydrothermal vents or cold seeps. These environments are localized, unstable, and short-lived on geological timescales. Organisms cluster tightly around them, forming dense communities in an otherwise barren landscape. The contrast is extreme, abundance existing only where chemistry briefly allows it. Elsewhere, scavengers dominate. Their bodies are designed to detect distant chemical traces, moving slowly until a signal appears. When food is found, feeding becomes frantic and disproportionate, followed by long periods of inactivity. Anatomy reflects this rhythm, expandable tissues paired with systems built to shut down for extended intervals. Reproduction also adapts to scarcity. Some species mature slowly and reproduce infrequently, while others release enormous numbers of offspring into the dark, relying on probability rather than precision. Time replaces speed as the primary variable. Success is measured not in efficiency, but in persistence. In such environments, time itself behaves differently. Generations overlap slowly, change accumulates gradually, and survival favors patience over adaptation speed. As depth increases, even these strategies approach their limits, leading toward regions where not just food, but predictability disappears entirely. Beyond 6,000 meters, the ocean enters a realm humans can visit only briefly and with extreme effort. Pressure exceeds 600 times surface levels. Temperatures remain near freezing, and the landscape is shaped by slow-moving geological forces. Trenches carve narrow wounds into the planet's crust, creating isolated environments cut off from most surface influence. Here, life exists at the edge of physical tolerance. Organisms found at these depths often lack features we associate with animals altogether. Bodies are soft, loosely organized, and sometimes difficult to distinguish from the surrounding sediment. Movement is minimal, sensory input is sparse, and growth is slow. These forms contradict the expectation that complexity must increase with survival challenge. Instead, simplicity dominates. Chemical analyses reveal adaptations at the molecular level that push known biological limits. Proteins remain functional under pressures that would denature surface enzymes instantly. Cell membranes maintain integrity despite constant compression. These mechanisms are observed but not fully explained, suggesting biology has pathways still outside our models. What makes this frontier unsettling is how familiar chemistry produces such unfamiliar outcomes. The same elements, the same basic cellular machinery, rearranged under constraints we rarely encounter. Appearance diverges not because life becomes exotic, but because the environment removes nearly every option except the ones that look strange to us. These deepest ecosystems are not just records of Earth's extremes. They serve as reference points for life elsewhere, on planets and moons, where pressure, darkness, and scarcity dominate. The more alien these creatures appear, the more they remind us that familiarity is a surface condition, not a universal one. As we descend through the ocean, alien appearance is not a sign of aberration, but of adaptation under narrowing possibilities. Each layer removes assumptions we carry from the surface, revealing forms shaped by constraint rather than preference. The deeper we go, the less biology reflects our expectations, and the more it reflects the environment's indifference. What remains unresolved is how much of Earth's living space still escapes understanding, and how easily our definitions of life collapse outside familiar conditions. The deep sea does not offer answers so much as perspective. It reminds us that our view of nature is partial, and that responsibility begins with recognizing how little of it we truly know.